So I'm happy to introduce next Joey Gonzalez and Reynold Shin from the AmpLab. Joey is a postdoc, and Reynold is a grad student.
Cool. Excellent. Thanks for having me. So I'm going to talk today about graphs, which we haven't talked about a whole lot, or maybe even at all. And so I'm going to talk about a project called GraphX, which is the goal of which is to bring graph analytics to Spark. So let's begin by some basic motivations. So I believe that graphs are essential to modern data mining and machine learning. We use graphs to identify influential people and information, find communities, understand people's shared interests, and model complex data dependencies. And so I'm going to give you a few examples now of these tasks at a very high level. All right, so one standard task in machine learning is maybe trying to predict certain attributes about a person. And so we think of maybe a social network. We'd like to predict maybe the political bias of the users on our network. And so a standard approach to this in machine learning would be to build a basic classifier that could look at the post of the individual and then try to predict the bias of that post. So for example, we could build such a classifier and apply it to these individuals, like that. And so for some of the posts, we might be able to predict the political bias. For others, it might be difficult, so we don't have enough local signal. And we could do that for these two users, and then based on sort of the aggregate signal from the posts of those users, we could then try to predict the political bias of that user, or at least make an estimate, like that. So on the left, we have the liberal, on the right, we have the conservative. And we could apply this technique to a lot of the users in our network. Those users that post frequently or have strongly polarizing comments, we might have enough signal to make predictions about them. But the reality is, for the vast majority of the users, we maybe don't have posts or don't have politically polarizing comments. And so if we just try to look at local signal alone, it's difficult to reason about their political bias. But fortunately, we have sort of side information. We have the context. And so if we look at these users in the context of their social network and try to reason about their political bias in the context of their communities, we can actually make more informed predictions. So we can set up models like conditional random fields and run algorithms like belief propagation on these graphs. And we can then sort of diffuse that signal across the graph and make better predictions. So that's one example of how we might use a graph. Another example is sort of when trying to understand the data encoded in the graph itself. So the graph structure reveals something about the community. And so one of the common algorithms in this area is triangle counting. And so in triangle counting, we're trying to estimate essentially the number of triangles associated with the vertex. So we look at the vertex here, colored in red, and we could count the triangles around that vertex. So there's 4 triangles associated with that vertex. And ideally, we could say that triangles are a measure of the cohesiveness of a community. So a user that has a few triangles is sort of like a center of a hub, hasn't really built a rich community around him, hasn't connected his followers. Whereas a user that has a lot of triangles relative to his number of neighbors has built a rich community. And so this is a way to sort of assess for each vertex its role in its community. Okay, and so another sort of more common or very important task today of graphs is collaborative filtering. And so collaborative filtering, we have a situation in which we have users. Here's pictures of people in our lab. And we have items, things that we're going to try to sell or market at least to these users. And then typically we have some kind of ratings. And so either the user has maybe clicked on a product or even provided sort of a quantitative value of their utility or preference for that product. And so we can set this up as a bipartite graph connecting users and items. And then we can use very simple algorithms to look at the graph structure and make predictions. So for example, if you want to figure out what to sell me, you could start with me. You could look at the graph structure. You could look at the things that I've rated, things I've given a score to. And then you could look at the items that were rated by, or the people that rated those items. So here's the other people in our lab. And then you could follow back and figure out what items they rated. And so in this particular example, a lot of people who like the things I like also like bikes. And so I might conclude from this data that bikes would be something to sell to me. And so that's, again, using this bipartite graph structure to make predictions about product targeting. All right, so there are many more graph algorithms. I'm going to put up a list. So there's algorithms in collaborative filtering. Alternating least squares have become pretty popular, and I think we might have mentioned that earlier. Some tasks in structured prediction. This is like the political bias estimation example I gave earlier. There's tasks in semi-supervised learning where I'm going to try to make predictions or to build learners across my entire graph. So using the graph to improve my ability to build machine learning algorithms. There's tasks in graph analytics. This is like triangle counting where I'm trying to understand the underlying structure of the graph. And then there's sort of more traditional machine learning tasks. Even classification can often be expressed as computation on a very large graph. All right, so now when we think about computation on a graph, we have to sort of think about it in the context of the systems we might use to do that computation. Now, traditionally, people use data parallel systems for everything big data, right? So there's your Hadoop. And this style of computation is you're going to process rows sort of independently and then compute some statistic. So there's a lot of parallelism. You compute some statistic. And this is actually pretty useful for a wide range of machine learning tasks. But for tasks on graphs, it's a little bit different, right? So when I'm operating on a graph is sort of an inherently recursive data structure. And that when I try to reason about a vertex, I need to reason about that vertex in the context of its neighbors. And so my computation sort of overlaps. So I have these vertices, and I'm trying to operate in their scope. So the neighboring vertices. And so this sort of pattern isn't as easily expressible, or maybe even as efficiently as expressible in systems like Hadoop and MapReduce. And so as a consequence, a collection of systems have emerged, Pregel, and then the missing one there is GraphLab, my system. A collection of systems have emerged to sort of address this type of computation. All right, so these systems targeted at computing on large graphs, sort of inherently follow this graph parallel abstraction, in which we define computation at the vertex level. So we define the logic of a vertex as a little vertex program living on each vertex in our massive graph. And then we constrain the interaction of these vertices to along edges in our graph. So neighboring vertices are going to interact. And in the case of systems like Pregel, these neighboring vertices pass messages to each other. So we can encode computation as this sort of process of passing messages along edges in our graph. And then in systems like GraphLab, the vertices operate by looking at each other's shared state. So that when I'm trying to reason about my political bias, I can look at the political bias of my neighbors and make an update on my value. Okay? And then parallelism emerges in this setting by running multiple vertices simultaneously. So I get parallelism from running the two vertices here at the same time. And a different system introduces constraints on which vertices can run simultaneously. So systems like Pregel allow all vertices to run at the same time, whereas GraphLab might introduce constraints that say neighboring vertices can't run at the same time. Okay, and so by exploiting graph structure, these graph parallel systems are actually able to achieve orders of magnitude performance gains over sort of traditional techniques for computation on graphs. And so the sort of example that I often give for GraphLab is the task of triangle counting. So here I'm going to look at how the GraphLab system, this is I developed for my thesis, how it runs in a graph, the Twitter graph. So this is a graph of 40 million users and 1.4 billion links. And so we can look at a Hadoop solution to this particular task. So this is a paper introduced to use Hadoop to efficiently compute the number of triangles in this graph. And I essentially count the number of triangles for each vertex, this task I described earlier. Okay, so they use 1,500 machines. They're able to compute 34.8 billion triangles. That's a lot of triangles in 423 minutes. So as part of my thesis, I developed a system called GraphLab, and it designed to sort of compute on graphs more efficiently. And so when we run the same problem, using 64 machines, we can solve the same problem in 15 seconds. So this is almost 1,000 times faster using fewer resources. There are a lot of reasons why this could be. Our system's in C++, there's a mix of Python and Hadoop. But the reality actually is we can go and look at the abstraction itself, and by changing the way we sort of look at graph computation, we're actually able to really reduce the amount of communication. And that's where the big win comes in. Okay. So there's been a big emergence of these sort of specialized graph processing systems, systems like Giraffe, which is the open source or the Apache version of Google's Pregel, the GraphLab system, which I developed as part of my thesis. Twitter has its own collection of systems. And so all of these systems really achieve this kind of improvement in performance by first exposing an API, which allows you to express computation efficiently for a graph, and then exploiting the graph structure to reduce communication and to more efficiently compute on that graph. Okay, so a lot of specialized systems. And so you might ask at this point, with all these big specialized systems, why do we need GraphX? Is it just to be able to do graph computation on Spark, or is there something more we can achieve? And so what's kind of neat is if we step back and look at the bigger picture, here's what it used to look like. So you used to use Hadoop to do a graph algorithm, and it would take a huge amount of time. And then came along systems like GraphLab, Pregel, and they really shrink the amount of time by orders of magnitude that you would compute on a graph. And so you'd say, well, we're done, right? We've squeezed the amount of time. But the reality is the full data processing pipeline isn't just graph computation, but there's an element of graph creation, which now becomes a dominant problem. And then post-processing, what we do with the final graph result. And so now when we look at this, we have to think, how are we going to address this full pipeline again? All right, so to give you an idea of how bad graph creation really is, I like to think of graphs as just a list of vertices and edges nicely formatted in a file. But the reality is graphs look more like this. It's a dump of XML, and hidden in it is vertices that maybe relate to the Wikipedia documents and links that relate to edges. And actually, this is a tame version of a graph, but still a messy version. And so we want tools to be able to process this. So essentially, the state of existing specialized graph processing systems is they're great at graph processing, but they're not so great at constructing the graph and then post-processing the results after the computation. And none of them are really interactive in the way that Spark is. And as a consequence, in order to do this full pipeline, I have to maintain multiple systems to solve these problems. Okay, so the cool part is that Spark really excels at these limitations. So maybe we can introduce Spark and address these problems. All right, and so GraphX, the project, tries to unify the data parallel and graph parallel view of these systems. So from Spark, we bring in the table API, the RDDs, fault tolerance, and task scheduling, which are really powerful aspects of Spark. And we combine that with the GraphLab technology, the ideas we developed in the GraphLab research, the Graph API, the graph representation, and efficient execution strategies. So we combine these two. And by doing that, we'd be able to build a single system that can address the entire pipeline. All right, so another cool consequence of bringing these two views together is that we can go between tables and graphs in a single unified system, allowing us to start maybe as user data living in a giant table, interpret that table as a graph, and then bring in information about product ratings, for example, joining essentially a graph and a table to produce a new graph, which we can then compute on running some sophisticated inference algorithms, and then ultimately producing a table which we could then feed to a front-end system or do future analytics on. So it's giving us a pipeline which we can seamlessly move between graphs and table views of data. So now actually going to try to jump into some of the details of the underlying GraphX system. And so to begin with, I'm going to sort of present how graphs and tables come together. So first, we can think of a table describing the IDs, the things, the vertices that we're trying to reason about. So here maybe we're reasoning about users, so our IDs are the usernames. And these correspond to vertices in our graph. So we go from a table to vertices. And then in that table, we might have attributes associated with each user. And those attributes become attributes in the graph. So attached to each vertex is the information that was associated with that row in the table. And then the graph structure is encoded in a second table, a table connecting pairs of vertices. Right? So here we have an edge between Reynolds and J. Gonzalez. And so we have an edge connecting R to J in our graph. Right? So we've gone from the table to the graph. And again, we have metadata associated with these edges. Maybe it's ratings, or in this case, it's the type of relationship between each of the users. Okay? And so that's how we can sort of look at a graph as a table and as a graph. And as a consequence, we are able to introduce this new Graph API. And a Graph API is sort of like an RDD, but it's an attribute graph, so it's a resilient distributed graph, really, which has attributes, again, associated with each vertex and edge. And the attributes have type V and E, so the user can define the type of attributes that live on the vertices and edges. And the graph initially presents a collection of very simple views as tables. So I have a graph. I can view the vertices as a giant table, which has a vertex ID and the attribute. The edges is a giant table, which contains the IDs of the source and dest and the attribute for that edge. And also is a table of triplets, which joins together the vertex attributes and the edge attributes on each row. So I can see the attributes of the user, the edge, and the other user. In addition to these sort of table views of graphs, we also provide operations to transform the graph. Things like the ability to reverse the edges, a very simple calculation. It takes a graph, produces a new graph with all the edges reversed. But also more sophisticated operations like filtering a graph by removing vertices and edges to construct a subgraph. Or operations like mapping the vertices and edges to new values, allowing us to change the values of the vertices and edges in our graph. We provide the ability to join graphs with tables. So this is a very useful tool to bring in extra metadata about vertices into our graph system. And finally, and probably most importantly, we provide a very simple computational primitive upon which we can build the existing graph parallel systems. And this is the Aggregate Neighbors function. So I'm going to try to now explain the behavior of this function in a little more detail. Okay, so Aggregate Neighbors is the underlying computational primitive graph algorithms as a whole. And so the way it works is, it's essentially, it could be thought of as a MapReduce job that lives on every vertex and operates over the neighborhood of that vertex. So to illustrate this, let's look at just vertex A. So I'm going to think about the computation just on vertex A. And the Aggregate Neighbors function has directionality. So I'm going to just consider the in edges to vertex A. So I'm going to look at this function as though it was run on just the in edges. And the first step in the Aggregate Neighbors is to take the user's defined function, a map function, which is executed on each edge, in fact, in parallel for the vertex A. And so that function is going to look at the full triplet on that edge and produce some result, some accumulate that's it's output from the map function, and then combined using the user-defined reduce function. So that reduce function takes pairs of these accumulates and produces a single value. And that value is placed back on the vertex. And so this aggregate neighbors function takes a graph and produces a new graph with the aggregate information of each of the neighbor of each vertex on each vertex. All right, so now here's a quiz question. So what would the function look like if I wanted to compute what is the oldest, what is the age of the oldest follower for each user? So give you a second to think. Okay, so here's what the function looks like. So I'm going to compute the follower's age using the aggregate neighbors function. So I have to define a map function and a reduce function. My map function takes the edge and and gets the source vertex and gets the age of that vertex and just returns it. So that's the map function. And my reduce function is just going to take the max of the two values. And so executing this and then saying dot vertices, getting the vertex view, will return a table which has the oldest age of the follower for each vertex. So if I wanted to know how many users have really old followers, I could do this and get an estimate of the age of the oldest follower. Okay. So what's really actually pretty crazy is that we can express systems, full systems like Prego and GraphLab, using just this aggregate neighbors function in conjunction with those earlier operators I described. And actually, in this case, in under 40 lines of Scala code, which is actually saying a lot. And so we actually built the system, and there is a prototype that people could, in theory, download. And in the current system, we actually use some cool ideas. So we borrow the techniques developed in GraphLab and Prego to allow us to really optimize the execution of this aggregate neighbors function and really all of the graph computation. And so we've done some additional things to improve performance of joins, local hash indexing, tricks to make it so that the graph computation can run quickly in an iterative setting. And so here's a very early result. So here we're comparing Hadoop, GraphX, and the high-performance GraphLab system, computing PageRank on a relatively large graph. And so this is the time for 10 iterations. And so already we see that sort of GraphX is achieving a compromise between Hadoop, where it's close to an order of magnitude faster. It's not quite as fast as GraphLab, but it's exposing all this higher level functionality. So that's one early performance result. But the cool news is there's actually a collection of optimizations still available to us that actually are only available because we have this high level view. So things like looking at the bytecode itself, we can decide when we need to bring all the triplet information together. So we can actually optimize data communication beyond what GraphLab was able to achieve. We can also look at execution strategies, things that look at how we iterate over vertices and edges to access them more efficiently depending on the structure of the graph or the type of computation. So there's actually some opportunity for cool optimizations. All right, so here's what we've currently implemented in our system. So we have algorithms like PageRank, connected components, shortest path, null training least squares. And we've built these on top of abstractions, which we've also built on top of GraphX. So we've implemented a Prego abstraction and a synchronous GraphLab abstraction on top of GraphX. And this all sits on top of the Spark substrate. All right, so Reynold has agreed to do a demo of GraphX, a live demo. So he'll come up and help.
Do you want to talk?
I can try to talk, yeah. Go ahead. Make it full screen, sorry. Cool, so Reynolds, here, we're going to ask that. So Reynolds launched a cluster of machines on EC2, which he can no longer log into.
Okay.
We can log into, great.
Okay. Cool. All right. So this demo is actually going to be, if you have ever seen any other graph system demos before, this one's usually slightly different from the rest of the systems you have seen. Usually,
Oh, it's off the screen. Can you make it slide in a little bit? Yeah. There you go.
Okay. what we're going to do here is we're actually going to go to the Wikipedia raw XML dump that Joey showed you on the screen earlier. And we're going to do ETL, extracting edges and vertices out of that graph, doing some filtering on that to grab only pages with the word Berkeley in it, and then run PageRank on it to find pages of the highest rank, which usually would take, I think, hours and hours to do on other systems. Where's that? But because I'm particularly bad at typing tons of stuff on the screen, I've actually had the code pre-typed that you guys can see, but I'll explain them one by one. Okay, so I have the Spark shell here launched. This is a Scala Spark shell, and hopefully most of you are familiar with it by now because of the exercise you have done before. So the first step is really just importing the packages of spark.graph. And the second step is I define this page hash function. So when Joey showed you the slides, there's this user ID or the vertex ID that's sort of defined by the username. He sort of lied a little bit to make it easier for you to understand. In the GraphX system, the unique ID for the edges and vertices needs to be an integer or long value. And in this case, I'm just defining a page hash that essentially just hashes a page title and hashes it to become an integer value. And next step, actually, I'm basically creating a new RDD called Wiki, pointing to the bunch of data on the Wiki, on a bunch of Wikipedia XML dumps on HDFS. And this is the same data set you have seen that Matei used for his demo. And we can do a quick count to see how many records are there. And if I'm not mistaken, it's over 10 million records for Wikipedia pages. All right, it's about 13 million records. So these are Wikipedia documents that we can take a look. For example, let's get the first document. Right, the first document is accessible computing. That says redirect to computer accessibility. And if you actually open this page on Wikipedia, it's going to actually redirect accessible computing to a different page. All right, so next, what I'm going to do is let's define the article class, which just represents as the title and the body of the text. And then I'm going to create an RDD based on the articles class. So what I'm doing here, just mapping each line, which each line in the raw dump I have represents one document. And for each line, I'm going to do tab delimit the line itself and create an article object. The article object, basically, I guess you can't see that either. Why? This is screen.
Yeah, screen has a question. Make it bigger in the slide window.
Actually, let me restart my thing. So let's get rid of screen. And hopefully nothing goes wrong. So let's define the Wikipedia. Let's redefine the page hash. And let's re-import the graph. And I'm going to create the articles class. Okay, so what I'm doing here is I'm splitting each line by a tab and then get actually the title and the body of the text and put it in, create an article object wrapping around it. And then have the collection of them becomes the articles RDD. And next, I'm going to create a vertices RDD that's essentially just filtering, using the articles RDD and filter out all the pages that doesn't contain the word Berkeley. And then I'm going to create a vertex object for each of them. In this case, the vertex ID is just a page hash, and the attribute of the vertex is just the page title. And next, this line is actually a little bit long. What I'm doing here, so if you remember in Wikipedia, basically each of in its markdown text, the way you link to a different page is you do 2 square brackets. And what I'm doing here is I define a regular expression pattern that matches for everything that has 2 square brackets. And I'm basing the articles. So for every article, I'm actually going to find all the links to other pages. And I'm going to create the collection of this is becoming an edges RDD. So I'm summing up all the edges. I'm creating our edges RDD that represent all the edges and all the outgoing links on Wikipedia here. Let's just create these edges. All right, next what I'm doing is it's too fast. It's bad when your system runs too fast. So what I'm doing here is I'm creating a new graph. And graph is basically just consists of, again, as Joey said, vertices and edges. In this case, I also added a small API called correct edges. And what it's doing is real-world graphs actually have a lot of missing values and have incorrectly constructed graph. For example, on Wikipedia, there's a lot of links that actually result in 404 pages. Somebody had a typo in the title, the pages they linked to. And so what correct edges is doing is actually it's going to get rid of edges that doesn't have the correct vertices they are pointing to. In this case, it's basically a short data cleaning step. So now I created this G. So again, G is just a graph of the edge type. And then I can run PageRank on it. So in this case, we had one of the Prego PageRank already implemented in our package. So I didn't need to write the whole PageRank again. But even if you had to express PageRank itself using the Aggregate Neighbors API, it's less than 10 lines of code. So I created the ranks graph. And now let's just try to print out basically. So remember, everything's actually lazily evaluated here. It's just following the Spark context. Everything's blazing fast so far. But the last operation is actually going to be more expensive because it's actually going to compute the rank and doing all those filtering we have done before. And what I'm doing here, if through yesterday's Scala training you can tell now, it's actually just computing the ranks of the pages and then getting back the result of the vertices, joining it with another graph, which is the ranks graph. This is the original, joining it with the ranks graph and the original graph. And then I'm going to get all the results back, sort them, print out pages with the highest rank. And remember, there was a filter we done before that contains only pages that contain the word Berkeley. So what do you guys think? Let me start running this. What do you guys think that, what pages that contain the word Berkeley have the highest rank on Wikipedia? Any guess? I'll give you a T-shirt. University. What's the second one? It's the city. I'm not even sure if AmpLab has a Wikipedia. Maybe one of you could do it right now, and we could connect Spark Streaming with this. So, right. So it's actually, I think it would make like some of the nerds proud. I think we're actually bounded by how fast we can transfer the log data from Amazon to this machine right now. Here you go. So UC Berkeley has the highest rank of 12, and Berkeley DB has a rank of 10.4, not bad for nerds. And then there's a bunch of other things that all have the rank 1.0. The reason is actually this graph is surprisingly sparse because it turned out pages have the word Berkeley in them. Doesn't really point to each other. But yeah, so this is sort of a quick hacky demo I've done here. And it's really the gist of it. This is a very sort of early work and work in progress. The gist of it is that this task used to take, I think, hours, maybe even days for you to get the data, parse the data, and being able to pipe in the graph system, run PageRank on them, and then collect the results, print you the highest ranked pages. And now you can do it actually literally in minutes. Yeah.
Cool.
Do you want to wrap up?
Yeah.
Now pass back to Joey for wrapping up.
Thanks. Yeah, I was afraid to do a live demo, so awesome. Okay, so that was a live demo. All right, so a quick summary. We've essentially brought the graph parallel primitives onto a system like Spark. It's currently slower than GraphLab, but there are a lot of ways that we can improve performance, and so there are a lot of things that we can hope to actually make it faster. In the meantime, it's also exposing a whole new set of functionality that's, I think, pretty powerful. And so, as I said here, we'll hopefully be able to bring performance closer in the near future. All right, so as Reynold said, it's still a very early prototype. I think we have a link to the GitHub, to Reynold's personal GitHub repo if you want to take a look at some of the early API code. And we're actually hoping to get this out by Spark 09, so that's the current plan, or 0.9. Okay, so any questions? Thank you.
Hi, I noticed that Titan is not on your list of other systems. Can you talk a little bit about why not, and if you've looked at it and what you found? Thanks.
Absolutely. So why not Titan or Neo4j? So right now, what we are looking at it as graph computation systems designed for doing the computation on the graph. Titan actually has some of that functionality, but it's primarily focused as a graph data storage system in basic data queries. That said, it would be actually kind of neat to introduce some of that Titan functionality into a system like GraphX. So that's something we're actually looking at.
Early on, you mentioned like belief propagation algorithms. What are the plans for those in terms of GraphX?
So what are the plans for belief propagation? So that's near to me. So my thesis actually was on parallel belief propagation in these large-scale systems, in particular GraphLab. I hope to be able to bring belief propagation to this. It'll be running in a synchronous form. But I think it's a nice primitive to be able to build analytics tools on top of. So belief propagation should be there soon. Mm-hmm.
Hi, Joey.
Hi.
Yeah, so I guess you might have already answered the question, which is to do belief propagation. So this is to do with dynamic Bayes network, where you've got asynchronous propagation, right? So you had these nodes. I thought that you could run them literally asynchronously, right?
Mm-hmm. All right, so what about asynchronous belief propagation? Right. Good question. So in my thesis, part number 2 is the importance of asynchrony in efficiently executing belief propagation. Unfortunately, GraphX doesn't yet support asynchronous execution. This is one of the sort of limitations that we're actually hoping to improve upon. To do that, we need to be able to introduce a degree of asynchrony into the Spark runtime itself. Dynamic Bayes networks are a little bit more interesting because they involve some degree of changing in structure or some growing structure, and that's something that we haven't started looking at, but that's something that we hope to be able to do as well. Mm-hmm.
Hey, really neat. So I'm wondering, for just really pedestrian uses, what's the technical leap to get it out of pure Scala and maybe have another interface?
To get it into release, or?
The technical leap to just get it out of pure Scala and have some other kind of interface to it, aside from just Scala command line.
That's a good question. I mean, it's available. So what is the hurdles to getting it to other API, other languages and other tools? So right now, it runs as a Scala API, which of course then works in the Spark shell. We haven't looked at supporting other things like Python, but I think that should be pretty reasonable, given that we can do it easily with Spark. So, yeah. Good question. Up front here.
I'm wondering if GraphX is good for semantic graph processing, so that
so is GraphX good for semantic graph processing? Are you referring to things like triple or RDFs or these classic semantic web tasks?
meaning edges has certain semantics, so
Yeah.
you can follow specific edges.
So actually, I think it is. So GraphX provides this triple value view of your graph data, and these RDF stores essentially are triple value stores. That said, Titan is sort of a system that was designed to be able to query these, same as Neo4j. As a graph processing system, that hasn't been our primary focus, but being able to branch out and do sort of queries against your graph, the semantic web sort of functionality is something I think we'd like to be able to do. So that's being able to find relationships that satisfy some predicate, like A is a friend of B, who's a friend of C, who also follows something, and be able to extract those local patterns in our graph.
So could you show that link for the
Oh, sorry,
GitHub
yeah.
repo again? And does it contain any examples, or if not, can you show us the demo code or put it up there?
Yeah, so we'll put some demo code up there. I think that actually links directly into the graph interface, the Scala code itself, not the source, the head of the repo. There will be a lot more development. And actually, I think we'll be moving to within AmpLab repo soon. So,
Okay.
But it'll be alpha, very alpha. More questions?
Do you have any techniques to deal with data skew, for example? There are some very popular nodes, and if you do MapReduce or you redistribute the data based on the number of connections, only one node will be doing really the essential work.
Yeah, that's a great question. So what about data skew on graphs? That's actually a serious problem. So our work in GraphLab addressed that problem. In particular, in PowerGraph, we looked at how to deal with these heavily skewed distributions of vertices. So it turns out, if you don't address this, if you look at real-world graphs, there's a small fraction of vertices that connect to the vast majority of the graph. And if you just try to treat them as sort of vertex records in their neighborhood, you find that many vertices have small neighborhoods, and some vertices have huge neighborhoods. And if you try to treat each of these things symmetrically, you'll get skewed performance in your system. What GraphX does is actually, although it gives you the illusion that you're processing at the vertex level, it's actually processing at the edge level. So we're partitioning the graph using the vertex cut technology from PowerGraph. So that's allowing us to, actually, I think I have an illustration of this. Yeah, so we're going to split the graph not along edges, but along vertices. And so this means that high-degree vertices become much less of a problem. So we're able to reduce the effect of skew. There's still going to be some skew in the balance of edges, but this can substantially reduce that. I say, actually, this is based on some techniques from scientific computing for sort of efficient sparse matrix multiply. So our partitioning algorithms are using these sort of techniques.
So obviously, it takes time to implement all these things in your platform, and there's a lot of mature graph algorithms out there already. Are you thinking about using some of those or re-implementing everything in GraphX?
So are you asking, are we thinking about reusing some of the existing work in graph algorithms?
Yeah.
Unfortunately, in order to take advantage of GraphX, it would have to be written in GraphX. Unless we could take, well, so I should step back a little bit. So things like GraphLab and Pregel present an API, and algorithms written against that API should be very easy to port to GraphX since we can expose the same API. But as it is, it would have to be ported to our Scala code base. So taking the code that I wrote for my thesis in GraphLab and porting it to GraphX is still slightly non-trivial, since it's a C++ code base, my thesis work, and the GraphX system is a Scala code base.
I was thinking also NetworkX, which is Python, but...
Oh, there's that too, yeah.
Right.
Is that it? Okay. Thank you.